Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 2.6, day 2, entitled Combining Functions. And today we're going to talk about this last objective, which is the composition of functions. And that's basically where you put one function into another function and then evaluate it. And that's what's being demonstrated here on this slide. So they're taking their two functions, f of x, which is the square root of x, and then g of x, which is x squared plus 1, and they are combining them into a new function, which they're calling h of x. And you don't really have to do that. You can write your composite function this way, where you have f of g of x. So that means you're going to take g of x and put it into the f of x function. So notice that they've left the f and then they put the g function into it, that x squared plus 1. And now they're going to put that whole expression, the x squared plus 1, into the f of x function, which was the square root of x. So you'll also see this written as f of g of x, written like that. And sometimes I like to call that fog. And you can write it the other way, where you have g composite f of x. So it's not really like a full-on O, it's kind of like a times that has an open circle instead of just a closed little dot. But just for fun, I like to call them fog and goff. And then this picture really does a good job of illustrating what's going on with the composite functions. You're taking a value x and you're putting it into the g function, and the g function is x squared plus 1. And then you take that and you put it into the f function. And the f function was to take the square root of that. So that's how they got the square root of x squared plus 1 as your whole output. And this is very nice and very simple to do with numbers, because you can take x and put it into the g function and get a number, and then take that number and put it into the f function and get another number out. So dealing with expressions is a little bit trickier, but once we're dealing with actual numbers, it's very slick and very fast. And here again, this is that composite function in this little chart at the bottom here. We have f composite g, or fog, of x. That's the same as f of g of x. So you take x and you put it into the g function, get an answer, and then take that answer and put it into the f function. So you start on the inside of those parentheses and work your way out. So you start on the inside with the g of x, and then you work your way out to the f of x. And here again, you read that as f composite g, or f composed with g. And then here they have a little circle and arrow diagram to show you this concept as well. So when you're dealing with f composite g, it's kind of like starting with x and going all the way to the end answer, instead of having to go to this, across this first little arrow to get through the g function, and then this other little arrow to get to the f function. So it does in one step what you could do in two smaller steps. So let's actually work with some composite functions now. So we have f of x equals x squared, and then we have g of x equals x minus 3. So those are our two functions. And we're going to find f composite g, and then we're going to find g composite f. And we're also going to find their domains. So for our f composite g, or fog, of x, I'm going to start on that innermost function. Remember, this can be written f composite g composite x, or f of g of x. So I'm going to start with that g of x function, like x minus 3, and I'm going to put that into the f function. So I'll have f of x minus 3, since that's my g of x function. And my f of x function tells me I need to square that stuff. So I will have x minus 3 squared. And then for the other one, for g composite f of x, I know we have the same variables, but we're going in a different order now. This is where we're taking g of f of x. So I'm going to take the f of x function and put it into the g of x function. So I'm going to do g of x squared. And the g function tells me I need to take x squared and then subtract 3. So you can see that just by switching the order, we get two very different answers. But our domain for each of them is going to be all real numbers. For the x squared function and for the x minus 3 function, I don't have anything that's in the denominator. I don't have to worry about taking the square root of something. They're in the numerator. They're just standard functions that I'm squaring and subtracting from. So my domain for both of them is just going to be all real numbers. I don't have any limits on any of the values for x that I could put in there. Okay, now for part B, they want us to actually evaluate these functions. So for f composite g of 5, I found that on the previous slide when we did f composite g, that was the x minus 3 squared. So my f composite g from the previous slide was x minus 3 squared. So now I'm going to take 5 and I'm going to substitute that into that function. So I'll have 5 minus 3 squared. So that's 2 squared, which is 4. Now, you could take 5 and put it into the g function, and that would be 5 minus 3, so that's 2. And then take 2 and put it into the f function, which is 2 squared, which gets you 4. So we did in one step what you could also do in 2 steps. And then for our g composite f function, we're putting 7 into that function. And from the previous slide, we found that g composite f of x is x squared minus 3. So I'm going to put 7 into that function where the x is. So I'll have 7 squared minus 3. So that's 49 minus 3, which is going to be 46. Now again, I could do this in 2 steps. I could take the 7 and I could substitute it into the f function, since I'm kind of working from the inside out. So if I put 7 into the f function, that would be 7 squared, which is 49. And then I would put that into the g function. 49 minus 3 is 46. So again, we're doing in one step what we could do in 2 steps. Now, hopefully from that previous example, you've also noticed that f composite g is not the same as g composite f. So just keep that in mind, that just because we're dealing with the same variables doesn't mean that we're going to get the same answers, because order matters. And the other note on here is that it's also possible to have multiple functions, more than 2. So here you could have f composite g composite h of x. So that means when you're evaluating this, you would put x into the h function and get an answer, and then put that answer into the g function and get another answer, and then put that answer into the f function to get your final answer. So again, you're working your way from the inside out. So let's do that. Let's do one of those big composite problems. So here we have f composite g composite h, and they're telling us that f of x is x divided by x plus 1, g of x is x to the 10th, and then h of x is x plus 3. So if I'm trying to find f composite g composite h of x, that's what I'm trying to find, I'm going to start by putting that h of x function into the g function. So my h of x function was the x plus 3. So I'm going to put that into the g function, which is the x squared. So that will get me, for my first step, x plus 3 to the 10th. Then I have to take that and put it into the f function. So my second step then is going to take this answer that I have here, the x plus 3 to the 10th, and put that into the f function here. Now I'm putting it in there wherever the x is. So I have x divided by x plus 1. So that means I'm going to have x plus 3 to the 10th over x plus 3 to the 10th plus 1. So that would be my final function. Okay, so far we've used composition to build complicated functions from simpler ones, but we can actually work backwards too. In calculus, you can actually decompose complicated functions into simpler ones. So that's what we're going to look at now in this example. So here we're given the function f of x equals the fourth root of x plus 9, and they want us to find the functions f and g such that capital F gives us f composite g. So we need to take that bigger function and break it down into its two smaller pieces. So basically you have to look at this function and you have to kind of ask yourself what's going on, what two things are happening. Well, it looks like we have an x plus 9 that's happening, and it looks like we also have a fourth root of x that's happening. And if I took this x plus 9 and put it into this function, then I would get out the fourth root of x plus 9. So if I wanted to start with the x plus 9, that would be my g of x function. And then I would have to put it into the other function, so that would be my f of x function. And then this would be my final f of x function, or my composite function. So there's my two smaller functions that make up, oh, what just happened? That make up the bigger function. Oh my goodness, my g of x function just went away. I'll rewrite it. There's my x plus 9. And my arrow went away too for some reason. Okay, let's try changing pen colors again. Okay, so there's my g of x function, and there's my f of x function. So if I started with g, like they want me to here, and substituted it into the f, like they want me to do here if I'm working backwards, then I would end up with my f of x function, my composite function. Okay, one last example then, where we're going to break apart our functions and have a little bit more of an application, is here in example 7. We have a circle that has a radius of 2 inches, and it starts to grow. And the radius is growing at a rate of 3 inches per hour. So we want to express the area A of the circle as a function of f of its radius r. So that's kind of wordy, but it says it wants us to express the area of a circle as something else. Well, I know the equation for the area of a circle. That's pi r squared. Now it says it wants me to write that as a function of its radius. Okay, well, instead of area being equal to this, I want the area to be a function. So I have to use f of something, and it has to be a function of its radius. So f of r will equal pi r squared. So basically, I'm just taking that area variable and rewriting it as f of r. So that means whatever value I plug in for the radius, I can find the area of the circle. Okay, and then part B says to express the radius as a function g of the number of hours, t, since the circle started to grow. Well, in the problem, it tells us that the radius is growing at a rate of 3 inches per hour. So for every hour, it grows 3 inches. So just basic algebra would tell us that that's 3 times t, 3 inches for every hour, and t is the hours. They tell us that here. And the circle started at 2. It started at 2 inches, and then it's growing the 3 inches every hour. So we're going to add on the 3t or add on the 2, however you want to think of it. Now that is actually what the radius is doing. It says the radius is growing. Okay, the circle had a radius of 2 inches, and now the radius is growing. So I'm going to set this all equal to r. But they don't want me to express it as r equals. They want me to express the radius as a function g. Okay, so instead of r equals, I'll have g of something equals, and let me just rewrite it as 2 plus 3t, since we started at 2 and then we're growing 3 inches per hour. Now my variable in the problem is t, and that was my time here, so I'm going to add g of t. So that's my new function for the radius. Now there's part C and part D on the next slide. So part C says we're going to write f composite g of t and interpret its meaning. Okay, so really we're going to write f composite g of t. So that means I'm going to take the g of t function and I'm going to put it into the f function. So I'm going to take my radius function and I'm going to put it into the area function. So instead of pi times r squared, I'll have pi times what my radius is, 2 plus 3t squared. Okay, so that's going to be my composite function. And then it says to interpret its meaning. So this is going to represent the area of the circle t hours after it starts to grow. Because we're putting t into this function. We put t in for time. If we put the time in, that will get us our radius. And then we can use that radius to find the area. So this represents the area of the circle, t hours, after it starts to grow. So you could give me any time past when the circle has started to grow, and I can tell you the area of that circle at that point in time. And that's what they're going to have us do for part D. Find the time when the area of the circle reaches 1,000. So basically we're going to work backwards now. Instead of putting in time to find the area, we're going to know the area and find the time. Okay, so using this equation from up above, using this function right there, there's a little arrow there, okay, we're going to find the time. So I'm finding t, and it says the area of the circle is 1,000. Well, that would be what this whole equation is equal to. This pi times 2 plus 3t squared, that's going to equal my area, because we just said this is the area of the circle. So I'm going to plug in 1,000 for that whole f composite g of t part. And then I'll have my pi times 2 plus 3t squared. And now I have to solve this for t. And it looks a little tricky, looks a little complicated, but it's not. I'm going to divide by the pi to get him out of there. And then I would have to take the square root of both sides so that I could get the squared out of there. So I'll have the square root of 1,000 divided by pi equals 2 plus 3t. And then I'd have to subtract the 2 and then divide by 3. So I can write that in two separate steps if you'd like. I'll have the square root of 1,000 over pi minus 2. And then I'll have that whole thing divided by 3. So my value for t will be the square root of 1,000 divided by pi minus 2 all divided by 3. And that you can actually do on your calculator. Now when you do this, remember you have to do 1,000 divided by pi and then take the square root of that answer. Because all that whole expression, the 1,000 divided by pi, that whole expression is inside my square root symbol. So don't just take the square root of 1,000 and get an answer and then divide by pi. Take 1,000 divided by pi, get an answer, take the square root of that, get another answer, subtract 2, get an answer, and then divide by 3 to get your final answer. And that'll be 5.28 hours. And again, we could change that decimal into minutes. So that would be 5 hours and 16 minutes. And again, you want to take the 0.28 times 60 to find out how much of that 60 minutes the 0.28 is. So the composite functions do have more application to them than what you might originally think. So make sure you go through these homework problems and practice those concepts. And if you have any questions, come on in and see me before school.